Right, here we are going to look at the last formula on the formula list. We're looking at the area of a triangle formula. Now, the area of a triangle here is given by a half AB sine C. So if I highlight those on the triangle at the top, I've got A, one side, I've got B, another side, and then this angle C is the angle contained by them. Okay, so this is used when we don't have the base and the height. So in yellow here on the triangle, I've marked on the height there. So that's what you're probably used to. The area is a half of the base times the height. We've got this other formula that lets us find the area when we've got this V shape. So two sides and the contained angle. So we don't really need to worry too much about the letters, just this V shape and the contained angle. So here we have got find the area of the triangle, give your answers to two decimal places. So we know the area is a half AB sine C, and we're looking for that V shape. So we've actually been given too much information here. We've been given three sides, we only need to substitute two in. We've got this angle here, so we need to use the two sides that are containing it. So the 4 centimetres here isn't actually required. The area is going to be a half of one side times the other times the sine of the angle containing them. We can now type that into our calculator. So a half-decent calculator will let you type that all in a oneer, and it'll spit out the answer for us. So we've been asked to round to two decimal places. So I've got 12.0451, so on. So whenever you've been specifically told to round, it's usually a good idea to write down your unrounded answer in maths. The area is going to be 12.04, but this 5 is going to force me to round that up. So 0.4 round to 0.5. This is an area. The sides are measured in centimetres, so your area will be square centimetres. So you need to have those appropriate units. Right, calculate the area of an equilateral triangle of side 2 centimetres. So no diagram here, so you need to think, what's that actually going to look like? Well, an equilateral triangle, that's a triangle with 3 equal sides and 3 equal angles. We've been told it's of sides 2 centimetres, so we know each side will be 2 centimetres, and each of the angles are the same. So my angle is going to be 180 divided by 3, which will give me 60. So each angle in my equilateral triangle is 60 degrees, a fact that you should hopefully know already. Now, we could, if we want, we could try splitting this down the middle, splitting it down here, finding the height by using a little bit of right angle trigonometry, but we don't need to. We've got this new rule, and we've got two sides forming a V and a contained angle. Now, I could have highlighted any two sides, and I've ended up with 2, 2, with a 60 between them. So I'm going to get the same area regardless. So my area is a half AB sine C. So my area is a half times 2 times 2 times the sine of 60. So I can put that into my calculator, type that all in a oneer in my calculator. And the question hasn't told me how to round off here, so I'm just going to choose 3 significant figures. So 1.73, because the 2 means I don't need to round up. The sides are in centimetres, so the area is in centimetres squared. Now, what you may be asked to do is something like this here, where we have got the area and we need to find one of the missing dimensions. So the setup looks very familiar. It's this sort of V shape, and we have been asked, well, we've been told the triangle shown has an area of 35 meters squared. So it's telling us the area. Find the size of the angle QRS. So it's this angle here. So we've got the setup that we've had in the previous 2 examples. We've got a V shape and we are interested in the angle containing it. So we're dealing with the area of a triangle. We've got this V shape. So my starting point is this formula. And now, same as I do whenever I'm working with any formula, is I need to plug in the numbers I'm working with. The area is 35. A half, well, that's just a half, times A times B, times 8.5 times 10, times sine. Well, I don't have a letter here, but what I could do is I could give it its name, times the sine of the angle QRS. I'm going to tidy this up a little bit, so I'll just figure out what that gives me. So I'll have 35 equals, so all of this here has given me 42.5, and I'm left with times sine QRS. Right, I want to get this on its own, so I get rid of multiplying by 42.5 by dividing each side of my equation by 42.5. So that will tell me the sine of QRS is 35 divided by 42.5. Now, as we saw with the sine rule, this will actually have 2 possible answers between 0 and 180. So I'll have my first quadrant answer and my second quadrant. Here, we can see by studying the diagram, we're going to have an acute angle, i.e. our first quadrant answer, the one that our calculator is going to spit out. But what I'm going to do for completion's sake is I'm going to show you what the obtuse angle would be as well. Right, the acute angle, QRS, is just going to be the inverse sine of this value here. So I can go ahead and type that into my calculator. So it's given out a big long number. Because it's a rounding question, I'm going to write down the unrounded answer. And I can just go ahead and round it off. So 4 significant figures, 5, 5, 4, 3, and the 9 is going to force me to round this up. So that's 55.44. We found an angle, so that will be in degrees. So 55.4 degrees, that's one of our acute solutions. There is, of course, for this equation here, there's going to be an obtuse one that's in the second quadrant, because, if we think back to our trig equations, sine has a positive value in the first and the second quadrant. And when we're dealing with a triangle, we could have an angle in the second quadrant, because that's between 90 and 180. So our obtuse angle, our obtuse QRS would actually be 180 take away that acute angle, and that will will give 124.561, so on. I'm wanting to round to 4 significant figures, so I'll have 1, 2, 4, 5, and then the 6 is going to make me round that up. So the obtuse angle will be 124.6 degrees, and that's the obtuse solution. Almost 100% of the time, so like 99% of the time, you'd be expected to find that acute. But if it does mention this being obtuse, this angle up here being obtuse, then you know how to deal with it. You deal with it like a trig equation, finding a second quadrant solution. Just to finish, I've just popped in a quick sketch of what this second solution would look like. So it is possible, this is why it is possible, we've got 2 triangles with the same sides, but our obtuse solution would look like this. Our acute solution, 55.44, is going to look like the diagram in the original question.